So in this video, we're going to talk about the spectroscopy specifically of aldehydes. And that's these first two exercises here in the homework. And then I'll have another video for the spectroscopy of ketones. Those are the second two problems in the homework. They're going to give you data from all the types of spectroscopy or spectrometry that we've learned so far. You'll have the mass spectrum, you'll have the IR spectrum, you'll have the Proton Nmr Spectrum, and you'll have the carbon-13 NMR spectrum. So you're getting data from all of those sources. Sometimes you'll get a unique piece of information from each one, and sometimes more than one type of spectroscopy will support the same structure. So they sort of give you the same information sometimes. Now the mass spectrum gives you the molecular formula. So that's what we're going to get from this first part of information. The IR spectrum tells you about functional groups: aldehydes, ketones, alcohols, carboxylic acids. The Proton Nmr Spectrum tells you about how atoms connect. Specifically, it tells you the different types of electronic environments that hydrogens are in. And the carbon-13 NMR spectrum does the same thing. It tells you how atoms connect, but instead of doing it through hydrogen, it does it through carbon. It tells you how many carbons are in unique electronic environments. And based on that, you can fit the atoms together to create those environments. So these are our pieces. Now, the first thing you want to do is to find the molecular formula. What atoms, what Legos do you have to work with? Only after you have that can you start to think about how those Legos are put together, either how the functional groups are put together or how the carbons themselves and hydrogens are put together. Okay. When you do a mass spectrum, you take a sample, you ionize it, you bombard it with electrons so it bursts apart, creates every possible fragment. But one of the fragments is exactly like your original molecule, except it has an electron missing, just one electron. That means that the mass of this fragment is going to be the same as the mass of the original molecule, so capital M to represent that. And as a whole, that fragment will have a positive charge because it's missing an electron, and it'll have an unpaired electron, meaning it's a radical, so that has a dot there. And if you remember, that is the symbol for the molecular ion. The molecular ion is the same molecule as in your sample. It hasn't broken or fragmented or crumbled apart. Same molecule as in your sample, it's just missing one electron. And so the mass of the molecular ion is the molecular mass, or the molar mass. Now remember, these are going to be given to you in M to Z ratios, that's mass to charge ratios. You end up, once you create these different fragments with their ions, you separate them using magnets and mass, and they turn a corner based on how big the charge is and how massive they are. Massive things have a harder time turning, and so they hit a detector after that turn at a different place than a lighter molecule. And so you're able to separate these ions based on their masses, and based on where they hit a receptor or a detector, you can tell how massive they were. Now technically, how much they turn really depends both on the mass and on the charge that they had. But the charges that are larger than 1, those create very unstable molecules that don't exist for very long. So in general, the charge, that Z, is +1, and so M divided by +1 is really just M. In other words, the M to Z ratio is really the mass. The M to Z ratio for the molecular ion is the molar mass for your ion. Now here they say that the molecular ion peak has an M to Z ratio of 58. So that means that our molecule needs to weigh 58 AMU, 58 atomic mass units. Or if you had one mole of it, that would weigh 58 grams. Okay, that's the first piece of information that we get from that. The second piece of information that we get from the mass spectrum that we use to find the molecular formula is a comparison of the molecular ion peak and what's called the M+1 peak. So remember, the molecular ion peak, that's the mass of the molecule. Except carbon does not always weigh the same thing. Every carbon has to have 6 protons, but different carbons can have different numbers of neutrons. If a carbon has 6 protons and 6 neutrons, then it is carbon-12. Now that's by far the most abundant element of carbon on Earth. It's around 98.1% of the carbon on Earth. But there's around, 98.9% of the carbon on Earth. There's around 1.1% of the carbon on Earth that has 6 protons but 7 neutrons, and so it has a mass of 13. Now let's think about our molecular ion peak. We were thinking that there would only be one molecular ion peak. That would be true if every carbon only had 12 AMU, only weighed 12 AMU. But sometimes, 1.1% of the time for every carbon that you have, the molecular ion will actually weigh 1 more than that. It'll be the mass of the molecular ion, but +1. The +1 is coming from the extra neutron in the carbon. That's adding 1 atomic mass unit. And so you'll get a tiny peak, the same as the molecular ion peak. It's still missing that 1 electron, still has the positive charge. It's based on the molar mass of the molecule, but the mass is going to be +1 because of that extra neutron. So if this peak for the molecular ion is 100%, you will have, and you only have 1 carbon, then you'll have a peak at M+1 that's 1.1% of that. So if this is 100%, this would be 1.1% of it, approximately. That's if you have just 1 carbon, because you only have 1 place where you're likely to have a carbon-13, and so there's a probability of you having that carbon-13 1.1% of the time. But what if you have 2 carbons? If you have 2 carbons in your molecule, then there's 2 places where you could have carbon-13. There's a 1.1% chance that it'll be on the left carbon and a 1.1% chance that it'll be on the right carbon. Overall, there is a 2.2% chance that you'll have a carbon-13 somewhere in that molecule. So if you have 2 carbons, the M+1 peak gets bigger, and it becomes 2.2% of the molecular ion peak. If you have 3 carbons in your molecule, now you could have a carbon-13 in 3 places. It could be on the first carbon, the second carbon, or it could be on the third carbon. There's a 1.1% chance that it'll be there. That means altogether there's a 3.3% chance that you'll have a carbon-13 somewhere. So that the M+1 peak would be even larger. It'd be 3.3% of the molecular ion peak. In other words, the percent height of the M+1 peak to the molecular ion peak tells you how many carbons you have. If the M+1 peak is 1.1% of the molecular ion peak, then you only have 1 carbon. If it's 2.2%, then you have 2 carbons. If it's 3.3%, then you have 3 carbons, and so on. 4.4%, then you have 4 carbons, 5.5%, then you have 5 carbons. So you can use the relative abundance of carbon-13 and the M+1 peak on the mass spectrum, the relative height of that compared to the molecular ion peak, you can use that to figure out how many carbons are in your molecule. Now here it says that the compound has an M+1 peak that is 3.3% as high as the molecular ion peak. That means that we have 3 carbons. Okay, so we've gotten the information that's useful from the mass spectrum. We've gotten the number of carbons and the overall mass that we need for the molecule. From that information, we could figure out the molecular formula. We know that we're going to have C3. We already know the number of carbons. We also know, so that we have carbon, we also know that the overall mass, so we have 3 carbons, each carbon weighs 12, right? I'm getting that mass from the bottom of the box on the periodic table. Each carbon weighs 12 AMU, so the mass we're going to have from carbon is going to be 36 AMU. The other thing we know is that all the mass of the overall molecule is 58 AMU. So we have to add other elements to our molecular formula to increase this mass. The most abundant element in the universe is hydrogen. It's the simplest element, 1 proton with 1 electron around it. Most of the hydrogen in the universe was created in the Big Bang. It didn't require stars to synthesize it. So it's everywhere. And even if you just think about water, which covers 3/4 of the surface of the Earth, there are canyons in the ocean that dwarf the Grand Canyon and that are submerged in water. You can picture how much water is on Earth. So we know that there's probably hydrogen in this molecule. Now, we have 36 AMU, we need 58. That means we're missing 22 AMU. Now, hydrogen only weighs 1 AMU. If you look at the box underneath, each hydrogen atom weighs 1 AMU. So if we need 22 AMU, we'd have to have 22 hydrogens. But there's no way that you can fit 22 hydrogens on 3 carbons. 3 carbons have a maximum of 2 times the number of carbons plus 2 hydrogens. So the maximum number of hydrogens you can have is 2 times the number of carbons plus 2. If you're thinking about the bonding, for every carbon you have bonds up and down, 2 bonds up and down. So 2 times the number of carbons, and then you have the 2 bonds at the end. So plus 2. That's the maximum number of hydrogens you can have. So here, if we have 3 carbons, it would be 2 times 3 plus 2, that's 8. Maximum 8 hydrogens can fit on these 3 carbons. 22 is way too many. So that means we don't just have hydrogen here. So we go to the next most abundant element on Earth. We know we have to have some hydrogen, but that's not going to be what we have the most of, or we can't just have hydrogen. So we use the next most abundant element on Earth in terms of likelihood, and that's oxygen. So what if we had 1 oxygen? Each oxygen atom weighs 16 AMU. If you have an oxygen, 16 at the bottom of the box on the periodic table. So 16. So we'd have 16 AMU coming from the oxygen. If you add that together with the carbon, that's 52. And so, if that gives us 52, to get a total of 58, because the hydrogen is 1, we would need 6. So that gives us 6 AMU. So if you add all of those up, that gives you 58 AMU. 36 plus 6 plus 16 gives you 58. In other words, the molecular formula for our compound is C3H6O. Really O1, but you don't have to write the 1. So now we have the molecular formula for our molecule. We got that from the information given to us in the mass spectrum. Okay, let's erase this, make some room for ourselves. Now once you have this, you can start to think about degrees of unsaturation if you want to. So for example, you may remember that the degrees of unsaturation is 2 times the number of carbons. So it's the formula for it actually was 1/2 times 2 times the number of carbons plus 2, that's the maximum number of hydrogens, minus, or actually plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens. So here, this is the degrees of unsaturation, so 2 times 3 is 6, plus 2, we don't have any nitrogens, we don't have any halogens, and we have 6 hydrogens. So here that's 1/2 times 8 minus 6, that's 1/2 times 2, that's 1. So we have 1 degree of unsaturation. We we either have one pi bond or one ring. Okay, so we have the molecular formula, and we also have some information about how these atoms are going to be connecting. We have to watch out for a pi bond or a ring. Well, we squeezed all of the information out of that mass spectrum like juice out of a lemon. So now we go on to the next type of spectroscopy, IR spectroscopy, and that tells us about the functional groups. Now in this chapter, we're going to be dealing mostly with aldehydes and ketones. So how can you tell those apart? Those are the functional groups. We can tell the difference between those using the IR spectrum. Now a ketone has a carbonyl with carbons on both sides. An aldehyde has a carbonyl with at least one hydrogen on one side. It could have a carbon on the other side. So there's only one bond that can tell these apart. And the bond is the bond between the carbonyl carbon and a hydrogen. The bond between a carbonyl carbon and a carbon, that's in both of them. The bond between a carbonyl oxygen and carbon, that's in both of them. The only bond that's unique is the carbonyl carbon to hydrogen bond. That bond absorbs between 2700 wave numbers. It casts a shadow. It absorbs the waves of electricity that hit it. At wave numbers between 2700 and 2850. So if you have an absorption in that range, that's a sign that you have an aldehyde. That's the carbon to hydrogen bond, the carbonyl carbon to hydrogen bond absorbing light. So that's one absorption. The other absorption, which they both will have, is the carbon to oxygen bond, and you'll remember that that absorbs, it's a sharp absorption at around 1700. Around there. We'll talk in more detail about that in spectroscopy in the next chapter, but that carbonyl carbon to oxygen bond will absorb at around 1700. So you'll know you'll have a ketone if you have an absorption at 1700 and nothing else. You don't have an absorption in this range. You'll know you'll have an aldehyde if you have the absorption around 1700, but also an absorption between 2700 and 2850. And that's the carbonyl carbon to hydrogen bond. So here, it says the IR spectrum of the same compound has a sharp peak at 1750. Okay, so we know we have a carbonyl, and that fits in with our degrees of unsaturation. We knew we had to have a pi bond. So now we know what it is. It's in the carbonyl. And it has a peak at 2750. That is between 2700 and 2850. That's a sign that we have an aldehyde. So already we've used these atoms up. We've used one of our hydrogens, one of our carbons, and we've used the oxygen. We got that information from IR spectroscopy. Okay. Now, there really is only one other way to put these atoms together, but let's think through the H1 NMR, the Proton Nmr Spectroscopy, to see what information that's giving us. I'm going to erase these other colors and things so that we don't get distracted. Okay, so it says the H1 NMR spectrum, the Proton Nmr spectrum of the compound has a singlet at around 10. And the integration for that is one hydrogen. That means there's only one hydrogen in that electronic environment. Now a singlet at 10, that is the signature of an aldehyde hydrogen. That's the shift for this hydrogen. It's close to the electronegative atom, so it's stealing electrons away, and there is the magnetic anisotropy that the electrons go in a ring, and they add to the external magnetic field when the electron density goes through the loop and underneath and over it, as we discussed in the NMR chapter. So because electrons are leaving, so you don't have shielding, and the magnetic anisotropy is adding to the external magnetic field, it takes a lot of energy to flip that nucleus with radio waves in the external magnetic field, and that's what this large shift number is telling us. The fact that there's one hydrogen there only confirms it. So those pieces of information confirm what we suspected using the IR data. We definitely have an aldehyde. Maybe if, for example, it would be hard to read that carbonyl carbon to hydrogen absorption. If, for example, this was somehow obscured in your IR and you weren't sure about it, this signal in the NMR confirms the presence of that aldehyde. Okay, next. It says we have a quartet at 2.2, there are 2 hydrogens in that, and a triplet at delta equals 1.1, there are 3 hydrogens in that environment. A quartet and a triplet is one of the 3 patterns that you want to remember. Remember, a quartet and a triplet, especially if the integration is 2 for the quartet and 3 for the triplet, that is an ethyl group. Oops, ethyl. So C, C. One of the carbons has 3 hydrogens, and one of the carbons has 2. The other patterns you should remember are if you have a septet and a doublet, especially if the integration is 1 for the septet and 6 for the doublet, that's the sign of an isopropyl group. And if you have a singlet with an integration of 9 hydrogens, that's a terbutyl group. But a triplet and a quartet, that's a sign of this very common branch, which is an ethyl group. And so the way this works, if you're thinking about, there's only one way that can connect to this carbon to give us all 3 of our carbons, all 6 of our hydrogens, and the oxygen. Let's think about what that splitting pattern means. These hydrogens in the orange, those are split by the different magnetic poles of the 3 hydrogens next to it. They split that into an n+1 pattern. Now in this case, the neighboring hydrogens are 3, and so that splits the signal for those 2 hydrogens in 3 + 1 into 4 peaks. And so those 2 hydrogens will show up as a quartet. A quartet. If you're thinking about the splitting for the other one, well, here you have 3 hydrogens. They have 2 neighboring hydrogens that are going to be, whose magnetic poles are going to be, you could have different magnetic poles for each of these, and that'll split the signal, the environments that those hydrogens are going to be in a population. So you have 2 of those. It splits it into 2 + 1, in other words, 3. These purple hydrogens are going to show up as a triplet. So we have a quartet and a triplet. The quartet has 2 hydrogens in it. The triplet has 3 hydrogens in it. And there's one other piece of information you could gain from this if you want to confirm your thinking, and that's the shifts. Remember that a CH2 normally appears at 1.2 parts per million. But it's alpha to a carbonyl, so you add 1. So overall, it would be 2.2 parts per million that you would expect this signal, 2.2 parts per million. The other carbon, that's a CH3, that normally has a shift of 0.9 parts per million. It is beta from a carbonyl. That means you add 0.2. Overall, you'd expect that at 1.1 parts per million, so 1.1 parts per million. So let's compare that with the information that the problem gives us. We have a quartet at 2.2 with an integration of 2. Quartet at 2.2 with an integration of 2. We have a triplet at 1.1 with an integration of 3. Triplet at 1.1 with an integration of 3. So you can use that other information to confirm your structure. Finally, you can use the carbon-13 NMR spectrum to further confirm your structure. Now, it says the carbon-13 NMR spectrum has 3 peaks. And what that means is you have carbons in 3 different electronic environments here. So let's get rid of this hydrogen data let's start thinking about the carbons and the environments that they are in. You have 3 carbons, and they each are in a different electronic environment. This carbon on the right is immediately attached to a double bond. It's in a carbonyl. That's one electronic environment. The carbon next to it is bonded to 2 hydrogens, a carbon, and it's alpha to a carbonyl. That's a different electronic environment. The carbon next to that is bonded to 3 hydrogens, 1 carbon, and is beta to a carbonyl. So that is yet another electronic environment. In other words, we have 3 electronic environments. And that squares with the carbon-13 NMR data. So overall, the structure of this molecule will be propanal. That beautiful, beautiful structure. So all you did was take a sample, it would be like a clear liquid, then you put it in 3 machines. You put it in a mass spectrum, mass spectrometer, an IR spectrometer, an NMR spectrometer, and a carbon-13 NMR spectrometer, and you are able to conceptually visualize the molecule. And once you have that picture, all the doors are open to all the conceptual framework that we built in this chapter. You have this, what can you do with it? Oh, you can treat it with a Grignard reagent, and you know what it'll become. Then you can oxidize it. Then you can do a maybe you can do a Wittig reaction with it and turn it into an alkene. Knowing this picture is a foothold to all the possibilities that you've learned in the reaction, in the synthesis part of the class. Let's do one more. We'll do this one a little more quickly because now we know what we have to do, so we know what we're looking for. We're looking at the mass spectrum. We're going to get the molecular formula from that. We're going to look at the IR spectrum. We'll get the functional groups from that. We have the Proton Nmr Spectrum. That's going to tell us how atoms connect, specifically how close the hydrogens are to each other. And then we have the carbon-13 NMR, which is also going to tell us how atoms connect. In general, NMR tells you how atoms connect. Okay, well, let's zoom in. Let's focus on the mass spectrum. What they tell us is that the M+1 peak is 4.4% as high as the molecular ion peak. That means that we have 4 carbons, as we discussed. Next, they tell us that the molecular ion peak has an MZ ratio of 72. That means that the total mass of the molecule has to equal 72 AMU. So, if we're trying to figure out the molecular formula, we know that we'll have C4, and we also know that whatever else we have, everything has to add up to 72 AMU. Now, if we have 4 carbons, we know each carbon weighs 12 AMU, so that's going to be 48 AMU coming from the carbons. 12 because that's the number, that's the mass of 1 atom of carbon given at the bottom of the box in the periodic table. Now, if we wanted to fit in the rest with hydrogens, each hydrogen weighs 1 AMU, we would need 24 hydrogens. Right? That would be 24 plus 48 would be 72. But there's no way that you can fit 24 hydrogens on 4 carbons. At most, you would have 2 times the number of carbons plus 2. You'd have 2 times 4 plus 2. You'd have 10. At most. No way you can fit 24. That means that we don't just have hydrogen here. We have to have something else too. Well, what else? The next most abundant element on Earth is oxygen. And notice, this is the molecular formula we get here is really more plausible than exact. It's likely, but not definite. To make sure it's definite, we use the data from the other types of spectroscopy. So we suggest something that's plausible, and then we test it with the other types of spectroscopy. Okay, so if you have oxygen, well, oxygen weighs a lot. If we just have one, that's going to add 16 AMU to our total. So 16 plus 48, that is 64. That means that we would still need 8 more. That's 8 hydrogens here. So you can check, you can do 48 plus 8, that is 56, and then add 16, and that gives you 72. So our molecular formula now we know is C4, H8, O. And really O1, but the 1 is implied just by writing the O there. You know, you have at least one of them. So that's our molecular formula. That's what we got from the mass spectrum. Okay, we're going to put that behind us. Let's focus on the next thing. The next thing is the IR spectrum, and that's going to tell us our functional group. Oh, there's one other piece of information we can get from this. Once we have this, we can find the degrees of unsaturation. So remember, that's 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of halogens, fluorine, chlorine, bromine, or iodine, minus the number of hydrogens. So here that's going to be 1/2 times 8, that's 2 times 4, plus 2 plus 0, we don't have any nitrogens, minus 0, we don't have any halogens, minus 8, that's the number of hydrogens we have. So that's going to be 1/2 of 18, oh, sorry, those are subtracting, 1/2 of 2, so that's just going to be 1. So we have 1 degree of unsaturation. That means we either have 1 pi bond or 1 ring, either one. At this point, no way to tell. Okay, so much for our mass spectrum. Now let's zoom in on the IR spectrum and think about the functional groups we might have. It says the IR spectrum of the same compound has a sharp peak at 1720. Sharp peak at 1720, that means we have a carbonyl. And it has a peak at 2775 wave numbers. Remember that if you have a peak between 2700 and 2850, that is the absorption, that's the energy that's absorbed by the carbonyl carbon to hydrogen bond. So the fact that we have an absorption in that range between 2700 and 2850, that's an aldehyde. Signal that we have an aldehyde. Okay, so we have an aldehyde. So much for the functional group. So much for IR. That also is confirmed. We know we had a pi bond or a ring. Now we know we have a pi bond. So that's the data we got from the degrees of unsaturation. Okay, now let's think about proton NMR. We still have 3 other carbons that we need to attach. Well, it says we have a singlet at delta equals 10, and the integration is 1. As we saw before, that's the signature for the hydrogen in an aldehyde. So if we had any doubt from the IR, if it was difficult to read the IR at all, this NMR is confirming that we have an aldehyde. We have the signal at 10, the chemical shift of 10 parts per million. It's 1 hydrogen there, that's the aldehyde. It's a big shift, 10 parts per million, starting from 0. And that's because the electronegativity of the oxygen is pulling the electrons away, so there's very little shielding here, and also the magnetic anisotropy is adding to the external magnetic field, so you need a lot of energy to flip that nucleus. Okay, so much for that first signal. Next, we have a triplet, a multiplet, and a triplet. So we don't have any of the patterns. We don't have a triplet and a quartet, so we can't just conclude we have an ethyl group. We don't have a doublet and a septet, so we can't conclude we have an isopropyl group, and we don't have a singlet with an integration of 9, so we can't conclude that we have a tert-butyl group. So instead, we have to think how we can connect these other 3 carbons. Well, we know one of the carbons has to attach to this aldehyde carbon. The question is, so this is a for sure. The aldehyde has to be at the end of the chain. The question is, will the other 2 carbons, branch off of that, or will they go in a straight line? Those are the only two possibilities. Okay, well, let's think. We have a hydrogen in one electronic environment, 3 hydrogens in a second electronic environment, and 3 more hydrogens in a third. Notice if you were just paying attention to the integrations, here you would have an integration of 1, 3, and 3. Now we don't have that. We have an integration of 2, 2, and 3. That's our first sign that this is not on this left. This is not going to be our structure. That's the first sign. We'll think about it though. Let's see if this other one passes that same test. Here we'd have 2 hydrogens. Next we'd have 2 hydrogens. And last, we'd have 3 hydrogens. Now in this case, if you're thinking about that same integration, we'd have an integration of 2, 2, and 3. That is what we find. We have 2, 2, and 3. Well, what if this, so far so good, but what if this is just a fluke? What if the structure is actually completely different and we're like way off the mark, despite all of our careful analysis? Let's check the numbers here and make sure, the splitting and the shift to make sure. Okay. This is next door to 2 hydrogens. That means it splits into 2 plus 1 or 3 peaks. In other words, it'll be a triplet. So you'll have a triplet. Next, CH2 normally appears at 1.2, but it's alpha to a carbonyl. So you add 1, and the shift will actually be 2.2 parts per million. And the integration would be 2. Okay. I'm going to go quickly like that for the next one. Here. This is next to 2 hydrogens on one side in one electronic environment, 3 hydrogens on the other side in a different electronic environment. Those will split it in different ways, and ultimately we'll have a mess. In other words, we'll have a multiplet. Now the shift for that multiplet, it's a CH2, so you would think that it would be at 1.2. That's the normal shift for CH2, but it's beta to a carbonyl. Beta to a carbonyl, that means you add 0.2, and so we have 1.4 parts per million where we'd expect that. The integration, again, is 2. Okay, last one. These hydrogens here are next door to 2 hydrogens. It's next door to 2, then it's going to split into 2 plus 1 or 3 peaks. In other words, it will also be a triplet. So a triplet, the shift, CH3s normally appear at 0.9, and it's too far from the carbonyl to feel any shift from that, so it's just going to appear at 0.9 parts per million, and the integration will be 3. So let's check to see if those values are the ones that are given. We have a triplet at 2.2 with an integration of 2. A triplet at 2.2 with an integration of 2. We have a multiplet at 1.4 with an integration of 2. A multiplet at 1.4 with an integration of 2. And we have a triplet at 0.9 with an integration of 3. Triplet at 0.9 with an integration of 3. So for sure, this is our molecule. Our molecule is butanal. Butanal. And once you have that conceptual picture of the molecule, all of the doors of synthesis are open to you. You could reduce it to an alcohol. You could turn the alcohol into a bromine by using PBr3. You could do an elimination reaction and a substitution reaction once you have that. Or instead of reducing it, you can oxidize it. Use sodium dichromate. It'll turn into a carboxylic acid. Or instead of oxidizing it, turn into an alkene with a Wittig reagent. All of the myriad possibilities, all of the creativity of a chef is open to you now that you have gleaned this conceptual picture from beeps and spikes of machines. So in these two exercises, we've done spectroscopy for aldehydes. I'm going to stop the video here, and then in another video we'll talk about the spectroscopy for ketones.